Okay, well, in the last section we talked about directional derivatives and gradients on planes. Now we're going to talk about them in space. And the procedure is really the same. So this should feel a little bit like review with just a slight addition to it. All right, so let's say we have some function, f of x, y, z, so three independent variables. And we want to know the derivative of this function that's in the direction of this vector. So what would be the derivative in this in the direction of this vector u? Well, the process is exactly the same. The derivative in the u direction is the gradient of f dot u, provided u is a unit vector. So just to make it general, u over the magnitude of u. So now, just in case it wasn't a unit vector, we're forcing it to be a unit vector. So again, this is exactly the same as the last lesson, which is saying that the directional derivative right here is the gradient dotted with our direction. So what if we wanted to find that? Well, we need to find the partial derivatives so partial derivative with respect to x is y, with respect to y is x, and z is 1. So at the following point, we'd have f partial x 0, f partial y is negative 1, and fc equals 1. So therefore, my gradient vector would be negative j plus k. And now we want it in the direction of this vector, v. So we need to take vector v and make it a unit vector. So 2i plus k all over root 5. So our directional derivative in the v direction equals negative j plus k dotted with 2 over root 5 I plus 1 over root 5 k. So at this point, now it's just a simple dot product. So this equals 1 over root 5, or root 5 over 5. So that's my rate of change. That's the instantaneous rate of change of this function in the direction of this vector. So here's just a definition, or rather a written definition of what we just did. The gradient f, or written like that as well, is the partial derivative with respect to x in the I direction, plus the partial derivative with respect to y in the j direction, plus the partial with respect to z in the k direction. And we have some properties of the gradient vector which are analogous to the properties that we learned in the last section, which are provided that f is differentiable and u is a unit vector, then our directional derivative is just the gradient times our unit vector, and we know that the gradient vector is in the direction of the greatest rate of increase of f. It's perpendicular to the level surface, and the magnitude of the gradient vector is the maximum rate of change of f at a, comma b, comma c. Okay, and these are totally analogous to 2D that we worked in the last video. All right, so let's consider this, this three-dimensional shape. We have f of x, y, z equals x squared plus y squared. The graph is down here. This is a bunch of concentric cylinders that are centered around the z-axis. So here's one level surface, but there are an infinite number of level surfaces. So if we wanted to find the following gradient, what we'd need to do first is find the partial derivatives and write an expression for the general gradient vector. So partial with respect to x is 2x and 2y, and this should have been a z, and that equals 0. So my gradient vector is 2x I plus 2yj plus 0k. So it just ends like that. So at this specific point, then we just plug that point in. So this is going to equal, putting in 0, we get 0i, and putting in 1, we get 2j. And that's it. So we see that here at point 0, 1, 1. So 0, 1, 0, 1, 1. We get this 2j, and this is this vector 2j right there, pointing in the j direction. And at the point 1, 0, 1, so at this point here, so our gradient vector at the point 1, 0, 1 is going to equal 2i plus 0j plus 0k. And so we get this vector 2i coming out. So the steps for finding gradient vectors, find their partial derivatives, find the partial derivatives, find the general gradient vector, and then just plug in the points. And again, what that vector does is it points in the direction of the greatest change, and it's perpendicular to the level surface. So a little bit more practice. Here we have a bunch of spheres, and notice that these spheres are all, it's negative, negative, negative. So as the spheres get bigger, what that means is we're increasing, the level surface has a greater negative value. So if we want to find the gradient vectors, we get the general gradient vector, which is negative 2xi minus 2yj minus 2zk, and we plug in this point, so this equals minus 2j minus 2k. And so that's the point 0, 1, 1. That's this point right here. And notice that our vector, the negative 2j minus 2k, this vector is pointing into the circle. And that makes sense because our level surface, as we go out, get more negative. And remember that our gradient vector points in the direction of the greatest increase. So it's pointing in because our inner circles become more positive. Similarly, at the point 1, 0, 1, so 1, 0, 1 is right up here. You can see our gradient vector pointing in, and let's find that. So that would equal, putting in the point 1, 0, 1, we'd have negative 2I minus 2K.
All right, let's look at an example here where we're dealing with level curves and level surfaces. So we've got our two functions, f of xy and g of xy, and if we consider this value to be z and this value to be z, then we have a bunch of four-dimensional graphs, which would be f of x, y, z. Let me write that again. So f of x, y, z, which is going to equal 4 minus x squared minus 2y squared minus z, and we have g of x, y, z, which equals 4 minus x squared minus z. So we could get the gradient vectors for each of these. So gradient f equals, and I'm looking at the three-dimensional piece, so gradient f is negative 2xi minus 4yj minus k, and del g, or gradient g, sorry, is negative 2xi minus k. And now notice, these are the gradients for the level surfaces, but if we were to get rid of the k component, which is the third dimension, then the green values, those are my gradients for the level curves. In 2D. Okay, so when it says the level curve, find a vector perpendicular to each of the following, well, vector perpendicular, those are going to be my gradient vectors. Because remember, gradient vectors are perpendicular to the level curve or to the level surface. So for part A, perpendicular to the curve at the point 1, 1, we're just going to put 1, 1 into there. So A, we have negative 2i minus 4j. And for B, the level surface, now we're looking at the three-dimensional gradient vector, so we're going to include this component. So now it's negative 2i minus 4j minus k. And notice that the I and j components are the same. And looking at C, similarly, the level curve at the point 1, 1, so we're just putting in 1, 1 for there. We get negative 2i minus, well, minus nothing, just minus 2i. And for D, now we're looking at the surface, so we're including the k component. Okay. So to give some perspective of that, it says, a hiker on the surface of this three-dimensional shape right here is at the point 1, negative 1, 1. So that's right here. And he starts to climb along the steepest path of ascent. So he's going as steep as he can. Now, in terms of the contour map, we know that the steepest ascent is going to be perpendicular to the contour. So what is the relation between vector grad 1 comma negative 1 and the vector tangent to the path at 1 comma negative 1, 1? Well, really quickly what we can do is we can get a gradient of f, which is negative 2x I minus 4y j. And at this point, 1, negative 1, grad f is going to equal negative 2i plus 4j. And we can see that here. We're going to the left. Let's see. Going to the left, meaning our x is decreasing, and then we're going up, which means my y is increasing. And it says, what's the relationship between the vector? Well, these vectors are going to be exactly the same, except for in 3D, I'm going to have negative 2i plus 4j plus my k component. The idea being that if we were to take this vector here and project it onto the xy plane, if we projected this vector onto the xy plane, what we're getting when we project that vector onto the xy plane is this vector over here. So what's the relationship between them? They're exactly the same, except for 3D, I've got a k component because I'm going upwards. Same idea here, same type of problem. We've got this 3D parabola, and this is what's the relationship between grad negative 1, negative 1, which we know is just negative, well actually it's just 2i, putting in negative 1 in for x here. So that's my gradient vector here, and we can see at the point negative 1, negative 1, we have a vector pointing just in the I direction. And in terms of the relationship between the gradient vector and the vector tangent to the path of the steepest ascent, well, this vector over here is going to be 2i plus some k component. The key thing being that, and this is what we're building to, the vector tangent to the path of the steepest ascent, what we're trying to get the idea of is drawing tangent lines to a surface so that we can soon start thinking about tangent planes to a surface. And here we are, tangent plane to a level surface. Well, suppose we have some four-dimensional system, and it's differentiable. Then an equation for the tangent plane to the level surface at some given point is the partial with respect to x, x minus a, plus the partial with respect to y, y minus b, plus the partial with respect to z times z minus c equals 0. Now notice, this is exactly the same as how we originally started thinking about planes. The idea is if we have a gradient vector, which is fx I plus partial yj plus partial zk. Okay, so let's draw. Let's say we have some surface here, and that's a level surface, and we've got at some point, here's our gradient of f coming out, and let's say that this is the point, that's the point A, B, C, right here, and then there's a point infinitely close to it. Let's call that x, y, z. It's a little messy. So x, y, z is very close to the point A, B, C. So we know that the vector x minus a I plus y minus b j plus z minus c k is a vector, this vector here, and provided that x, y, z, and a, b, c are very, very infinitely close to each other, that vector is in the plane that is tangent to the surface. So this vector here is tangent to the surface. Therefore, if we were to dot these, and let's call this T for tangent vector. So if we were to dot the gradient vector times our tangent vector, this is going to equal 0. So therefore we get, and when we dot it, this is the equation that we get. That's the dot product of the two, and it's set equal to 0. So let's look at an example of that. Let's find the equation of the tangent plane to the sphere at this given point. So we say, well, del f is the following. And then if we plug in our point 1, 2, 3, we're dealing with 2i plus 4j plus 6k. That's my gradient vector. So my tangent plane, so this is the plane that is tangent to the sphere at this point. So let's see if we can try to draw this. So we've got some sphere here. Talking about the so at the point 1, 2, 3, at this point here, we have a vector that's going 2 in the x, and then 4 in the y, and then 6 in the k. So this vector here, something like that. And it's perpendicular to our surface. And what we're looking for is the plane, and here's the hard drawing part, but the plane at this point that is the plane that's tangent to that point. So this is the plane here that just touches this point once and then bounces off. So the equation for that plane is going to be 2 times x minus 1 plus 4 times y minus 2 plus 6 times z minus 3. And that equals 0. So that's how you find, not hard, that's how you find the equation for a tangent plane to a level surface. Okay, let's do just a couple practice problems, and that will be it. So we'll just do one of these. This is find a vector normal to the surface and an equation for the tangent plane at the surface. So we know what to do here. Let's find a gradient vector. So our gradient vector, well, first of all, just to be most careful, let's write this as f of x, y, z equals, and now so x squared minus xyz minus 3. So the gradient vector 2x minus yz I minus xz j minus xy k. So those are the partial derivatives, and then plugging in the points, this equals negative 2 minus 2 I minus 2 j minus 1 k. Simplifying that, we've got our normal vector, which is just our gradient vector, negative 4i plus 2j plus k. So that's our vector normal to the surface. So the equation for the tangent plane is going to equal, so the tangent plane not write it like that. Our tangent plane equals negative 4 x plus 1 plus 2 y minus 1 plus 1 z minus 2. And again, just so that we're clear, these values are coming from here, and these values are coming from our point. All right, these problems are actually easier. So now find the gradient of the function. Let's do number 3. So the gradient of the function, well, we could write this as, let's just leave it like that. So f partial x is just e to the x plus y plus z. That's the derivative of it. And that's also the derivative of f partial y end of f partial z. So our gradient function, which is the direction that is in the greatest change, equals e to the x plus y plus z I plus, let me just fill this out. So this is interesting because each of the I, J, and K components are the same, and that's due to the fact that their partial derivatives are all the same. So let's find a gradient at a given point. So let's do number 15. So first, find their partial derivatives. Let's just jump right to the gradient vector. That's going to equal, let's see, yz I plus xz j plus xyk. So taking all their partial derivatives and now plugging in the point. So we get, there's y and z, so 6i, and then x and z, and then x and y, so plus 2k. So there's my gradient at the given point. All right, so last example here. Now we want to find the directional derivative. So remember, directional derivative means the instantaneous rate of change of this function at this point in this direction. So we'll just do one of these. So we're talking about how quickly is this function changing at this specific point when you move in the direction of ijk. So the first thing we need to do is find the gradient vector. So grad f is yi plus xj plus 2zk. And we're talking about at the point 1, 2, 3, so that is as follows. So there's my gradient vector. And the directional derivative, remember, the directional derivative equals the gradient vector dotted with the unit vector in the direction that I'm going, so in the ijk direction. Well, we need to find the magnitude of this so that we can get a unit vector, and we know that that's just going to be 3 because it's 1 squared plus 1 squared plus 1 squared. So our unit vector is 1 over root 3i plus 1 over root 3j, and we should rationalize these, but I'm just leaving it as is for right now. So there's my unit vector, and so the directional derivative in the direction of ijk is going to equal, dotting these, 2 over root 3 plus 1 over root 3 plus 6 over root 3. And if we feel like being good math students, we will rationalize it. So this ends up being 3 root 3. And that's the instantaneous rate of change at the point 1, 2, 3 in the direction of ijk on this given function. All right, thanks for listening. Hope that made some sense.